My talk today is on, is there value in acquiring high trace density seismic? First, let's start with the high level current state of industry. There's some things that don't change. Investors are always asking for better returns on their wells. Traditionally, wells have been drilled that often didn't make geologic sense. The geophysics was used to identify geohazards, not really horizontal well placement. The focus was on completions, and geomechanics really wasn't considered important. Shales are thought to be homogeneous, and so a cookie cutter approach was taken to pad placement. In the present day, focus is now shifting towards developing of current assets by improving drilling results, increasing production with less wells drilled. Prime example of this is in the Montney. From 2019 to 2020, 30% less wells were drilled with a 5% increase in production. Less wells, increased production, we're drilling better wells. So to continue down this path, we need to acquire goal-oriented seismic, not necessarily better seismic. So as geoscientists, we all want better data. Why? Well, crisper images, easier to process, fun to interpret, and frankly, it's cool to have high resolution data. So then why don't we always acquire high density seismic? Well, it's economics. So as business-driven geoscientists, the better data must provide by increasing production, reducing risk, identifying new sweet spots. To image shallower, you need to be able to add stacked pay to your well, maybe mapping of aquifers that if they provide economic value. So what is the economic value? Well, you need to quantify that for your seismic program. And you can do it through things of if they positively affect net payback, BEP, NPV, IRR, or other economic measures. Then that leads us to what are the economic goals of our seismic program? Well, that is defined by the team's goals. What does the team expect from their goals? Well, do we increase production? Can we reduce risk by imaging shallow geohazards, identifying sweet spots, improving the geomodel, or frac design? Yeah, notice at this time, I have not mentioned the standard geophysical terms, such as AVO inversion, fracture analysis, slip sweep, and so on. That means we need to think differently on how seismic can address our team's goals. It really comes down to thinking less about full stack, more about seismic products. And what are the seismic products? Well, seismic products need to address our team's goals. They need to discriminate lithology and fluids, determine fracture orientation, identify structural components such as subtle faults, use as a guide to populate rock properties for a geomodel, and identify sweet spots based on all the above criteria. So where do seismic products come from? Well, they come from our well-known and loved tools, seismic tools, partial stacks, AVO reflective attributes, seismic inversion, gathers, fracture analysis. And when we apply these tools, we like to identify anomalous behavior from these tools and then tie it back to the production on our project area, just like machine learning. Now let's talk about cost versus value. Now we need to address that all seismic is not created equal. It is true that the cost per trace of high density seismic is significantly less than cost per trace of traditional seismic. But, and more importantly, the cost per square kilometer of high density seismic is typically significantly higher than the cost per square kilometer of traditional seismic. Therefore, a business case must be made to justify that additional expense. Now I like to look at this whole cost of seismic, capital cost of seismic thing in a step progression. You start with your economic goals. Those are dependent on the seismic products needed. The seismic products are heavily dependent on the acquisition parameters, and the acquisition parameters control the cost of the seismic. So you must know the acquisition parameters for reaching the team's economic goals before you can accurately get a cost estimate. So then we need to start with our goal determination. That's where it all begins. How do we determine the goals, objectives that will maximize your company's return on their seismic investment? Now we like to group that into a three-step process. 1, economics. 2, imaging. 3, operations. Now let's start with economics. Understanding your team's economic goals what factors will impact that? Well, increasing your NPV, reducing your risk. And that comes down to relating then the economics to the geology. Identifying the geological features that minimize risk and maximize NPV. So really you need to avoid those geological features that reduce production and need to target those geological features that increase production. So how does seismic fit into this? Well, you need to look at this from two perspectives. How is your seismic currently being used to reach your team's goals? Both successes and the failures. Actually, the failures are more important because they can help you identify potential uses of higher resolution data and hopefully, or maybe, turn those previous success or failures into successes. An example of that is in geosteering. If you use geosteering to steering a well, traditional seismic, it helps you keep your bore in place, or your drill bit in place, and keep it in zone. Now, if we had higher resolution, could we keep the drill bit in zone a greater percentage of the time? That's the question that needs to be asked. What will be that increase in production by keeping it in zone longer? Another example is subtle faults. If we can image smaller faults, that will help us reduce our risk in our drilling program. What is that economic impact on your drilling program versus the cost of higher resolution seismic? Also, how about your resolution of your geomodel? Identifying these sweet spots, identifying the edges of sand channels better, like we see in this graph here. In B, you can see that we're not really defining the edge of that sand channel, whereas on A, the increased trace density is really helping us define that edge. And on a bigger scale, understanding the geology and engineering on a larger scale, that can really impact your project positively. So we're really correlating here geophysics to geology. Higher resolution will give us imaging thinner beds, higher density traces, defining horizontal stratigraphic changes. Smaller near offsets, imaging shallower. You can kind of get the picture here, and there's a list of additional items here that show you. So we've clarified that more is better. It helps. It will give us better imaging to reach our economic goals. But how much is enough? What resolution detail is required to reach those economic objectives? As a team, you need to define how small a fault is small enough to help us reach our economic objectives. How much do we need to increase the detail and resolution of our geology to reach our economic objectives? Now we need to quantify that, and in terms of our economic goals. And once we determine that, we go to the next step. We know what we need out of our economics from the geological resolution. Is it geophysically possible to achieve this level of detail and resolution from your seismic within your project area? That leads us to imaging. First step is we need to understand the data we do have. Do we have 2D, 3D, VSP? What's the vintage? In a perfect world, we'd love to have a higher resolution 2D data set to help us understand what the ceiling is of our resolution for that project area. But that is often not the case. So now we're going to start talking a little bit about seismic program design. I like to separate it into 4 technical components. 1, spatial sampling. 2, recording patch. 3, line spacing. And 4, near surface. In spatial sampling, it's pretty simple. What we need to determine is the maximal usable frequency, or Fmax, based on all the existing data we have. Raw data, stack data, everything we have. Once we figure that out and we get a look at it within the project area locally across, because that can change significantly, we need to determine, now, is that ceiling that we're seeing related to the Earth, or is it related to our data? We need to make that distinction, because ideally what we want to do is increase our spectrum, because the broader our spectrum, obviously the more increased resolution we will have, and that will help us reach our economic objectives. And the net result is we want the maximum resolution possible in the project area. The recording patch, well, that depends on seismic tools required. If you're after inversion, you need to understand your critical angle, your offset for density term. Fracture analysis, more about making sure we have a square patch and we have the right azimuths in place. AVO, understanding near far offset stack, and actually determining you're identifying any AVO potential. Now, example of that will be in the Alberta Deep Basin. Traditionally, data was acquired to 30 degrees. You can see the blue line on the gather to the side here. Now, you can see that there is a class 2 AVO anomaly at target zone that wouldn't have been imaged in traditional data. Now, at some point, that data was modeled, determined that there was value in that seismic data was acquired. End result, economic value was added because that increased the economic goals or improved the economic goals of the project. Lastly, line spacing. I want you to think about it as less about fold and trace density. It's more about near offsets and quality near offsets, not quantity. Poor near offset statistics can greatly reduce the quality of inversion results. Well, what are quality near offsets? Well, offset and azimuths that are statistically well distributed. And there's one way to get that. It's reducing your line spacing. Unfortunately, that's the parameter that probably costs the most to improve, but it is. So what are low quality near offsets? Well, that is when your offset and azimuth statistics are redundant. So that would be like reducing your shot or your receiver interval. Now that is often seen in, say, a vibe project when we half our shot interval. We hugely impact our trace density, but we have very minimal impact on our near offset distribution. So where are we at now? Well, we've now gone through this analysis. We understand the geophysical limitations of our data through survey design and modeling. Now, how do we determine the optimal parameters from a geophysical perspective? How I like to do that is through the law of diminishing returns. We know as we increase our trace density, our resolution is going to improve, our data quality is going to improve to a certain point. That's the part of the green curve. You get into the yellow and the red, the data quality improvement is going to significantly decrease. We need to find that sweet spot because that is the optimal geophysical parameters. There's no point going past that, in my opinion, because there's limited value in it and it just costs a lot more money. But optimal geophysical parameters does not mean optimal business parameters. If your seismic tools you need to reach your goals are inversion and rock properties, well, maybe you want to be higher up on that green part of the curve. If you're more interested in the simple geology, basic mapping, well, you probably only need to be down the lower end of that green curve. An example of that is back to the sand channel imaging here. If you look at A, B, C, as we improve our trace density, we're better defining that sand channel. When we go to D, you can see we've doubled the number of traces, but we really have not impacted the edge of the sand channel. Hence, probably not a lot of economic value in making that step in your data. So now we've established our economic goals quantifiably from a geology perspective. We know the maximum resolution of data that we can get out of our survey area. If that works, and it's theoretically possible to reach those economic goals, then we go to the next step. And the next step is operations. Now that's when we start to talk about high density. So first off, we need to understand the parameters that we've come up with at this point are a range. The resolution, the shot and receiver interval is a range. It varies. It's not exact. Same goes for your near offsets. You can have many combinations of receiver line spacing and source line spacing that will reach your geophysical and economic parameters that you previously defined, as well as your far offset. You define your minimum patch required. So how can we combine these parameters in a fashion to be as cost effectively as possible? Well, that's an optimization problem. And there are many optimization factors. There's a few that I've listed here, and we'll go into a couple of them to talk about briefly. One, program size. On a larger program, we can increase the efficiency by adding vibes. It takes time to get all this vibes going, get them synchronized, and get that amazing production that you can get these days. And it takes time and effort, and you need a big project to make that happen. You can acquire high density seismic in a small program, but you're not going to get that high efficiency, high production. Operational effects from a terrain perspective, you have slopes, vegetation, ground conditions, permitting, and environmental regulations. All these are important and will impact the time spent by the acquisition company in the field. So if we can do anything to our parameters to optimize them in a way that reaches our technical objectives, economic objectives, and minimize that time, it's well worth the effort. And there is many ways that can be done and have been done to do that. Now the last one I want to talk about is source type, receivers, dynamite, and fiber size. In Viber size, receivers cost more for an individual vibe point. In dynamite, a dynamite point costs more than a receiver. So those are our limiting factors. For vibe, the limiting factor is receivers. For dynamite, the limiting factor is our shot points. And we want to minimize our time in the field. So we need to make that work optimally to adjust our acquisition parameters so we can optimize them for those limiting factors. And I like to run into a little bit of an optimization comparison here on Vibe to see how this can work. So in Vibe, we want to reduce our cost per trace. Well, we can do that by increasing our number of VPs and decreasing our number of receivers. And you can see I have a graph here on the x-axis. We have the number of receivers in the project. As we have more receivers, our project costs will increase. And on the y-axis, I have limited offset fold at target. And as our limited offset fold at target increases, our near offset statistics will improve. Now, if we plot two parameters on here, A and B, you'll see that they both have roughly the same number of receivers, but one has a significantly higher limited offset fold, which means for roughly the same cost, you can significantly improve your near offset statistics. Now, a couple assumptions I've made in this analysis is I am assuming single sweep vibe, and as well I'm assuming that the biggest cost to this program is the number of days spent in the field by the acquisition company. Now, there's a practical side to this where this could be a value, and that is if you have a project area and you've gone through the economic goals and proven that the seismic can image these economic goals, at least from a modeling and design perspective, the economics will work, but management buy-in is tough. Now, there is a potential solution that can help in that step, and that is if we could minimize the cost per square kilometer increase of a higher density seismic and do it in a step approach to prove it out over time. And here's an example where we've put a whole bunch of parameters on one page, and you can see here each blob represents a different parameter set. The size of the blob represents trace density. Bigger the blob, higher trace density. The color represents a shot interval with a constant receiver interval. Now, what you can see here is two parameter sets I've chosen. One, I'm going to call a traditional dynamite program where we have less shots than receivers, and the other is a typical vibe program where we have more shots than receivers. Now, they are essentially the same parameters, we just have inverted ray pass. Now, what you can see if they were acquired as a vibe program, a 32% decrease in the number of receivers, which really means in the end, the acquisition crew is in the field less time because there's less equipment to move, means you'll have a significant decrease in your costs. Maybe not 32%, but there will be a decrease. Now, let's look at this from a perspective on the economic goals from a perspective that we looked at previously here. And we put in our blue and our green. Our blue shaded area is our traditional goals. Our advanced goals are in our light green. And that's based on our previous analysis. Now, if we add in black areas here, which represent poor line aspect ratios. Now, what I refer to in that case is source line to receiver line is greater than 2:1, or vice versa. Those are technically inadequate, and so we've thrown them out. And you can now see where the parameters sit, our 200 by 300 vibe parameters sit. Now, what we'd like to do is zoom in and have a closer look at this and see if we can get our parameters into that advanced goals area, but not spending very much more money. And let's look at one example here. There's a parameter here I've selected of 150 by 270. It reaches the start of the advanced goals in the range that we previously defined. Now, what's interesting about this is it's a 10% increase in number of receivers. So that's a increase in cost, but it's not a huge increase in cost, and it may be palatable by management. So that part is good. But how do we improve our data quality? Well, if you look at on this graph, we have a 46% increase in near offset fold. That's a significant increase in near offset statistics. So really what we're looking at here is we've significantly increased our near offsets for a minimal cost increase. Now, this could allow an opportunity to prove to management of that increased value of seismic for more advanced goals. Now, in conclusion, should I be acquiring high resolution seismic is probably not the right question to be asking. I think a better question to be asking is, how can we maximize the economic value of seismic to help our team reach its economic goals? Now, how we can do that is in a three-step process. One, we need to define the geology with the greatest economic impact. Two, we need to determine the geophysical limits of the data in the project area. And if that works, and if it's theoretically possible to reach the geology of the greatest economic impact, then we move to the operations side. That's when we can start talking about high definition seismic and high resolution seismic. Now, in the end, we'll have a cost estimate. And that allows us, at this point now, we can actually determine what the economic value is in acquiring seismic for a project. Now, as geoscientists, I feel we need to begin with the end in mind from Stephen Covey's 7 Habits. Our end objective is not to have cool, awesome data, although it's nice. Our goal is to acquire the seismic that most cost effectively helps our team reach their business objectives. Now, for acknowledgements, I'd like to thank my co-authors, Brian Schulte and Matthew Allen, for all your help. I really appreciate it, and thank you for everything. As well as to my amazing partner in life and business, Carrie. Thank you for everything. I don't think I could have put this all together without your help. Thank you, and thanks for watching.